Welcome to the lecture. The lecture actually is supported by IEEE Biometrics, and their special program is Distinguished Lecture Program. And this time we invited Professor Yagi to give us a talk on gait recognition. So let me introduce Professor Yagi a little bit. I think most of you know Professor Yagi very well. Professor Yagi currently is a professor in Osaka University. And I think most of you all know the data set created by Professor Yagi's team. And we should be the largest one in gait recognition.
One of.
Yeah.
Recently, there's many other.
Yeah.
Your data set is also one of the biggest.
Yeah. It's a very, and the data set contributes a lot to the research community. And Professor Yagi working in Osaka University for more than 20 years, right?
Exactly.
Yeah. And
more than 30.
Yeah, 30 years. Okay. So, so Professor Yagi also, in gait recognition, we all know Professor Yagi is a good researcher, a professor, and his team contribute a lot to gait recognition. And he is also our advisor of the competition. We are organizing the fifth competition, and Professor Yagi is the advisor. He also gave us a lot of suggestions on the competition. So since most of us all know Professor Yagi very well, I will just give more time to Professor Yagi to introduce their work. So welcome.
So thank you very much for my introduction. So my name is Yasushi Yagi from the Osaka University. So I belong to the computer vision area more than actually 40 years. 45? Well, I forgot it. Then half of my life, research life, my research topics is robotics. And also I made a special sensor called omnidirectional camera. So I proposed a world first omnidirectional camera. Then half of my research life is more focused to the pattern recognition and also computational photography. That two topics is the main topics. Then also we apply our computer vision technology to the healthcare and the medical. So that is our progress in my team. Then today's main topics is gait recognition in my laboratory. And title of today's talk is what can we know from gait? Not only focused to the clinical investigation. I also show you some result to different applications. So actually, today's my talk is consists from these four topics. First three is a diversity of observation. As you know, when you apply the gait recognition to the several problem, there's many diversities. For example, one of the diversity is a cross view. View is if viewing direction is changed, all of the appearances, human walking appearances also change. That is one of the difficult problem. Second is occlusion. In the real environment, there's many such kind of situation. It's caused by limitation of the field of view, or some case is there's some object, obstacles, then we cannot observe full body. Another topic is uncertainty of annotation. So this is not a popular topics, but when you build a new data set, in that case, everybody need a level. To get a level, you have to annotate it. So annotation is actually a very important problem in AI. So I give you these three topics first. Now after that, I show you a little bit different gait application that is applied to the medical and health wellness field. Then especially I'm focusing on the cognitive impairment detection. So let's enjoy today's my talk. And one thing, if you want to know a detail, let's send me an email. I forward your email to real researchers. That means the PhD students or other young researchers. So, okay. First, I'd like to start from the introduction of Gait. Maybe today's most of the people all know about Gait, but I don't know who know about the Gait. So first, I would like to talk about the Gait. So human gait. So how there's a differences appear. So here's a three man working. So all of them is was my student. Age is around 23 or 4, Masako student. Then all of them we observe from side view. But how about the walking style? Is it same? Maybe no. So this kind of the differences come from caused by personality. So here's a more easy to understand. There are these subject A, B, C. I show you a silhouette of Gait that get a video. So walking style is changed, start from right to left. So for example, there's a differences appear on the stoop. Subject B is he is healthy and back side is very good. Another difference is appear on the width of the stride. Another one is arm swing size. So this kind of the difference you can easily to feel. Another very interesting one is asymmetry. In case of the subject B, he only swing the right side. He never swing left side. Maybe we don't know the reason. I don't know the reason, but I can guess. Every day he bring baggage on left side. He use a shoulder bag on left side. So they do not have such kind of in his daily life, he never swing left side. Every time he swing right side. So such kind of daily habit change walking style. Totally, gait recognition is a person authentication from the gait personalities. Sorry?
So,
Too high?
I mean, the camera. Yes.
Good. Now, okay, I see. Okay. Then why is the gait recognition needed? There are many biometrics. So as you know, DNA, fingerprint, vein, such kind of the biometrics is very famous. But such kind of the biometrics, for example, in case of the fingerprint, we should have to touch the sensors. In case of the iris or face, in that case, we should have to stand in front of the camera. On the other hand, how about the gait? One of the good point of the gait is authentication at a distance. We don't have to stand in front of the camera. Gait can be authenticated at a distance from a camera, and any direction is okay. You can see here that image resolution quite low, and also he wear a mask. Face recognition doesn't work due to a heavy occlusion by mask, but the Gait can do it. That is one of the advantage. And already Gait recognition applied to the clinical investigation around 2008 or 9 in UK and also Japan. And in Japan, our technology already used at the Japanese police. And also, our technology is one of the used at the Japanese court at one of the evidence. Okay, now I show you a typical pipeline of gait recognition. First, we get input image sequence. So typically, we require more than one gait cycle. What is a one gait cycle? So gait is a walking. Walking is as you know, left and right, left and right. That is a walking. That means left and right. That is a one period. Then that is a physical motion. So that means gait cycle means left and right. Such kind of period is one gait cycle. So at least one gait cycle we get it. We can apply the gait recognition. Of course, if we get a long sequence of the MSC, of the gait, we can do more robust result. We can get it, but at least we required one. After we get a gait cycle, we apply the pre-processing. Normally, what we did is we set detect the human and also segment human region. Then we extract the gait features. So you can see here, this gait feature is a very famous one, GI, gait energy image. Then this kind of the gait feature do not use texture information. They use only silhouette. After we get gait features, that's easy to apply the classification. That is a typical gait recognition pipeline. And why not we use color or texture information? The simple answer is gait recognition is not a personality identification because people's clothes every day change. So color or clothes style cannot use. So this kind of the silhouette is mostly used. So one thing is gait recognition is actually not the same as a person de-identification. Of course, this kind of the silhouette gait feature can be used for person de-identification. Okay, I will show you one of our early CNN-based cross-view gait verification technique. So our technology, this early work, we prepare two networks. There's a left one and right one. There's a two network, and then after that we combine these two by square level fusion. Why use this kind of the two network? Reason is come from the cross view. In case of the small angle difference between the probe and the gallery, you can see here, face position is almost same position. So that means pixel or patch-wise difference is very effective for evaluating the difference of the gait features. So that means we calculate a difference at the input area. Then we input to the network. Then on the other hand, in case of the large angular difference, you can easy to see two guys' human face is not the same position. So considering this kind of the difference between a matching pair at a higher level of network architecture after obtaining insensitiveness to a spatial displacement. So higher level means just before the contrasting loss. So we combine the two different types of the network, then fuse these two networks. That is our first work using the CNN. Then here's a result. You can easy to see. CNN base is drawn by blue color. and red color, orange color is the baseline. And real line is a small angular difference case, and the dotted line is a large angular case. You can see here, in case of the baseline approach, if there's a large angular difference, we couldn't get a good result. But our CNN-based approach showed a very good result. So such kind of the approach is very useful for this kind of the cross view. Here is another approach is the identification problem. Identification problem is 1/n matching. So there's many people in the gallery, and if we get one probe image, we match with all of them, and then which one is the same. That is a task. Normally, it can be applied to the ID-less access control or person re-identification task. Before talking about the identification method, I'd like to compare what is the difference between identification and verification. This table is a distance between the probe and the gallery. I show you a small case, middle case, and large case. Then this black is probe, and the red one is the same persons in the gallery, and blue one is a different person in the gallery. And smaller case, nearest gallery is actually this red one, so that is the same person. And also, in case of the verification, we set the threshold circle over this symmetry, then exactly. So in that case, this different person also detected. So that means that is a false acceptance. So then in case of the middle case, nearest gallery is this one. It's okay. Then some other different person is far from the probe. So not inside this threshold circle. So both is acceptable. But in case of the large case, in case of the verification, nearest gallery is far from here, and also outside, and that means a false rejection. And in case of the identification, it's no problem. So identification verification has a different meaning. So different network structure is better. So our network architecture for identification is using the triplet loss. So triplet loss is a very useful tool. Triplet ranking loss. Ranking means we compare the same subject from the different view direction. And we also compare the same person and different person. Then if we input all of them, then calculate the symmetry of the same subject and the symmetry of the different subject. And then this order is very important. Relative similarity score are very important. Then same as verification, we prepare the large angular difference network and also a small angular difference network. Then we combine these two by square level fusion. So by using this kind of network, you can see here, triplet ranking loss shows a very good result for identification task. Of course, this work is 2019, 5 years ago, long time ago. But anyway, that time it shows a very good performance. Okay, so I show you about the previous slide. The meaning is a cross view. That is such kind of the difference, and also depend on the task. But anyway, we need a special technology. So I'd like to show you one of the difficulty. That is interpersonal variation. So even the same individual can look different depending on the lighting and the pose. You can see here, this is all of them is the same person, but input images seems to be not same. This is one of the difficulty, variation within the same person. Gait is a dynamic biometrics authentication. Normally, it has a large fluctuation. So there are the various factors that cause fluctuation, and we must always consider how to handle this kind of the intra-personal variation. So if the intra-personal variation can be shown by this red distribution, and this distribution is a smaller than different person distribution, blue one. In that case, that is an important point. And we defined a new loss function. Before that, we inspired by this word. This is a loss function considering a variation with a safe person. So they use a triplet loss and named batch all triplet loss and batch hard triplet loss. Both of them is considering the dissimilarity between the sample in the batch. And all triplet loss considering all samples. And batch hard triplet loss only consider the hardest samples. So, for example, in case of the all triplet loss, we try to bring closer the same class. Then keep away all of them. So compare all of them. That is all triplet loss. On the other hand, batch hard triplets only focus the hardest situation. Hardest situation means in case of the same class, only focus to the fastest pair, only evaluate for loss. And in case of the different classes, only evaluate the closest pair. So this is a hard triplet loss. Then the batch all triplet loss and batch hard triplet loss are loss designed for identification scenario. So inspired by this kind of the work, we extend to this work to the verification situation. So very simply, we propose a batch hard contrastive loss. Loss function considering intra-person variation suitable for person verification scenarios. So standard contrastive loss is only consider we set the margin and bring closer the same person and also keep away a different person. But in case of the batch hard contrast loss, we only consider about the hardest case. So that means this blue one, blue arrow shows that we try to keep away. Then on the other hand, the same classes we bring closer. So very simple way, but this is very effective way to improve the accuracy. So we apply this kind of the loss to the standard network, complex network, and the right network also. Here's a result by using our data set. First one is a right network. You can see here our batch hard contrast loss shows the best performance. And also next two is we're using a Gait set and Gait GL. So both case batch hard contrastive loss shows the best performance. So yeah, a little bit change the network loss function, we can get a good performance.
I have a question. Is there a problem of non-fair data set?
Oh, it depends on, of course. Then
because this technology is very successful in the long-tail challenges.
Yeah.
A hard sample replace the means.
Of course, that is the situation, and batch hard is sometimes a little bit sensitive compared with batch old. So it depends on. Okay, so there's a many challenging problem. We tackled to the several problems. One is a view angle. I already mentioned you. Another one is a closing difference, and another carrying object. Another is a walking speed, and a little bit different topics is a raw frame rate, especially applied to the real environment. Not so easy to extract high frame rate image. So low frame rate is most of the convenience stores camera. Such kind of the camera is a low frame rate. So that means not so easy to feel the motion. Many we propose several technology against the this kind of the challenge. But today's I am focused to the occlusion problems, gait recognition under occlusion. So occlusion is often appear. For example, upper case is low height age is here, and legs is we couldn't observe the legs. And bottom one, three image that is caused by the limited of camera field of view. We couldn't observe the upper body, and sometimes the occlusion area is changing. So such kind of the situation is sometimes happen. Then the lack of the body shape and pose and motion information that make drop the gait recognition performance. So how to tackle to this kind of problem is a very important one. Then we propose recent our technology occlusion aware human mesh model based gait recognition. So this work is also inspired by some study. This is one of the study, full body awareness from partial observation proposed in the ECCB 2020. In this case, 3D human mesh recover from a partial image. Only part of the body is visible. So this technology is very useful technology. Partial HMR uses simple self-training strategies to obtain the SMPL human model and directly from the single partial image by HMR model fitting framework. Then our approach is focused to the such kind of the technology. Imagined by such kind of technology, we combine the human mesh estimation and gait recognition in an end-to-end framework. So we only crop the occluded body part as an input. For example, in this case, only a lower body. Then human model estimate network estimated the SMPL parameter. So human model estimate network estimate the SMPL parameter. Then extract the pose and shape feature. Then after that, we do recognition. That is our end-to-end framework. How to do it? So our group proposed end-to-end model-based gait recognition technique we call the model gait. ACCP 2020. Model gait is a model-based method design based on the HML network, which regulates the SMPL human model parameters. If we in this case, we require full body data, RGB sequence. Then encoded, then we apply regression and extract the estimate parameters, camera parameter, and also shape and pose. And each frame shape data, we also calculate average shape estimate the average shape. Then from pose, we extract the 3D and 2D joint information. Then we combine all of them. Then we do a gait recognition. So at that time, this is a state of the recognition performance on non-occluded gait sequence. Then we change that framework to the occlusion case. So input is occluded RGB sequence. Sequence encoded first estimated in initial SMPL model. Then next, difference between the occlusion pattern in the input sequence may lead to different human model estimate, even for the same subject. So we only have the this kind of the partial image. So that means the estimated parameter includes some error. So we first estimate the phase of the input sequence and then synchronize the phase among sequence in order to compute the intra-subject pose variation in the same phase. So we try to synchronize phase. Then these input extracted shape and pose data is synchronized. After that, we apply the, but still this one is occlusion dependent body parameters. So we apply the attenuation transformation. So attenuation probation is actually the this part. Then we calculate the we reduce such kind of the variation, then get a more good shape pose. And from that one, we finally extract the shape and the 3D joint information. The average the shape parameter and pose feature obtained from a 3D joint location are used for recognition. We changed our model-based gate to this kind of the framework. Then this is a occlusion attenuation part. So in this case, in case of the to the shape and the pose parameter become more similar for the input from the same subject, where we define the paired similarity loss to minimize such intra-subject variation after attenuation. So we have this kind of the two network, and we pairwise and paired we define a paired similarity loss and minimize it, minimize the inter-subject variation of the body. By using this kind of technology, we apply to our data set. We have a full body multi-view large population data set. And then from that data set, we prepare this kind of the occluded image. One is a fixed occlusion at the top, only lower body is observed. And another one is a fixed occlusion at the bottom. Only we can observe the upper body. Another case is changing occlusions. So left one is upper body is occluded, and right side one is lower body is occluded. Then the changing the occlusion ratio. We prepare this kind of the data set. This is one of the result. We visualize the SMPL. You can hear this one is a ground truth. We estimate from the full bodies. We have the full body data set, so we match the full body. By using the full body image sequence, we extract the estimated model. Then the render one. Then this is estimated by model gate. So model gate requires a full body. In that case, you can see here, not so easy to estimate. There's a large error is occur. On the other hand, this is a new technology. We can get almost similar to the ground truth. This is another case. You can see here, it show, yeah. Then this is a comparison with a general gait recognition method. So occlusion case is our new fusion technology show good performance. This is equal data rate. Okay, so I skip this slide. Okay, so next I would like to talk about what can we perceive from gait. For example, not only applied gait recognition applied to the several tasks. For example, we know her from gait. That is a gait recognition, person identification. Another thing is her gait looks young. She should be in the 20s. So this is estimated age. Another is her gait looks beautiful. This is an aesthetic attribute. Another is she has a gait disorder. She may suffer from some disease. This is a medical application. Gait can be applied to several topics. So this is very famous demonstration by Queen's University. Oh, sorry. Video do not work, so I skip this slide. But anyway, Gait includes several information. There's some possibility to estimate several different things. So this work is aesthetic attribute, estimate aesthetic attribute from Gait. What is okay? Which Gait looks nice? How do you think? Upper one is good. Top one is good. Okay. Maybe most of the people feel the top one is good, more beautiful and more cool. But I think you can easy to feel if you I saw these two movies. But how about this one? Can you rating this working is worse or better? Not so. Someone feels good, but someone do not feels good. So annotating absolute attribute is not a trivial. And that criteria also depend on the annotator. So this is very difficult problem. But in case of a relative attribute, so how about previous case already all over you understand? If you compare these two, maybe you can easy to select. So relative annotation are relatively easy to do instead of absolute annotation. So that is one of the technology, how to annotate it to the data. So handle the relative attribute in deep learning, we need a special network. For example, if the input is a GEI, first is a key of this framework design of loss function, which is suitable for relative attribute. How to define? We prepare the network and the parameter of each stream of network share. Then we calculate the absolute scores. Then after that, we subtract these two. Then we define this as a relative score. And we use this one for loss function. This kind of definition, we do it. But actually, not so easy. Here is a certainty in annotation. For example, in this case, this left number is annotator's number. There's 7 annotators. All of them select second one. So that means voted to the second. But in this situation, how did you? all of the annotators' decision is not same. It's not so easy. Split it. So even if we give this kind of two image, sometimes not so easy to select. So and also it depends on the annotator's skill. So this kind of the problem we should have to solve. So we defined, we propose a new technology, annotator-dependent uncertainty-aware estimation of Gait relative attribute. What we did, we have a two-part. Actually, the first part and the second. First part is annotator-independent uncertainty rate. So first one is annotator relative attribute uncertainty model we prepare. So absolute score we calculate. Then from these two, we calculate the relative score distribution. Then from that, we can get a relative level distribution. This is annotator independent. Then second one is annotator dependent uncertainty rate. We model the skill of annotator. This transition matrix defined each annotator's ability. Then we use these two and calculate relative level distribution. So this relative attribute distribution normalized by the skill of each annotators. Here is one of the experimental results. So vertical axis is annotator. Then the horizontal axis is level. Then if this pattern is very close to ground truth, in that case, good performance. If this pattern is very far from the ground truth, in that case, not so good. So I show you one of the baseline methods, but compared with that, by using the method, pattern is more close to the ground truth. So this kind of the annotator difference, how to handle is also very important. Of course, it depends on the problem, but anyway, that is one of the important issue. So from this kind of, in this case, we give the attribute is beautifulness, cheerfulness, and relax, or some these kind of 5 attributes we prepare. Then compare by using the 10 annotator. Then the performance is better than previous method. Okay, and this kind of the method is already a demonstration at the Umeda, Osaka. Place to demonstrate it in the center of the Osaka. And when someone work, and here's some character, wellness, and there's some, once more I show you.
Okay.
That number is the estimated age. Age and attribute is shown at there. So this kind of demonstration we did. Okay, so finally my talk is about the medical application. Name of our this paper is a PPGCN, new network, phase aligned periodic graph convolution network for dual task-based cognitive impairment detection. Dementia, that is a big problem in the world, especially elderly people. Dementia is a progressive disease. It is uncurable. And dementia can be delayed by proper medical intervention. So important point is early stage detection. So we tackle to the this kind of the problem. By the way, the very famous ankate is MMSE. That is a medical use, mini mental state examination. That is a very simple test. Do an ankate, then the total score is 30. Then if score is larger than 27, that is healthy, and between 23 to 27 is MCI, and also lower than 23 is dementia. So very simple test, but the problem is that take 10 to 15 minutes, and also need a questionnaire, so co-medicals, and the question are fixed. So that means the subject may memorize the answer. So that means it cannot be applied to daily use. Normally, 6 months interval is required. And another big problem, the accuracy is not so high, actually. So if we have the more accurate method, we can easily to detect the MCI. And also, yeah. Then we create a new technology, that is a dual task working system. That is dual task is a combined cognitive task and behavior task for detecting of a low cognitive status. So in this case, stepping action and answer to the question. We combine these two. The question is very simple. You can see here. First, we do a step interaction, and after that, show a calculation. So in this case, 100 minus 7. Then erase the screen. Then the show two answers. Then user select one of them. That's such kind of the very simple system. Then from the cognitive score and also athletic score, we combine both of them, then estimate. Then our test is one cycle is 80-second test. Then we try 3 times. One time is also accuracy is higher than MMSE, but if you do 3 times more rows, we can estimate, and accuracy is more high. Then actually, this is a framework. PPGCN, we extract, first we extract this kind of the pose. Actually, we use a RTM pose. Then extract 17 joints features. Then each joint features, we can get this kind of the signal. Then pose network, we have a pose network and also cognitive network. Pose network input is 70 joint angles. And the cognitive score is input for cognitive network. This is a very simple on CNN. And this pose network is a little bit new idea. What is the new idea? So you can see here, this is one of the joint information, right knee up and down stepping motion. Left side is a healthy subject, and right side is MCI or dementia subject. You can see in signal shape is completely different. So dual task, if you give such kind of task, MCI people or dementia people cannot continuously do a task. So in this case, their working patterns has some cannot do a periodical motion. So then we extract the stepping action is also 2 steps is 1 cycle. So we extract each period. Then we align the phase. So after we extract these kind of sequence data, we align all of data to this kind of 3D space. So two axes is phase and period, and the vertical axis is amplitude of each joint. Then compare these two. Healthy subject and the MCI subject has a different type of the pattern. From this kind of the pattern, we discriminate. Then we prepare the special network. Such kind of a trial we did 3 times. So for the input is a 3 trial, and 3 trial input is input for our network. Then in our network, we have the convolution about the phase convolution and spatial convolution, and also a pedicle convolution. Then we get the result. The total network is something like this, and the pose network, we extract the pose feature, and from the cognitive network, we get the cognitive features. We concatenated these two features. Then after that, the fused network calculate both of them, and finally, we discriminated MCI or dementias and healthy people, positive and negative. You can see here, accuracy is quite high. We do a cross validation, and average score is sensitivity and specificity 0.92 or 0.93. This is quite high compared with the previous test. Then the accuracy is 0.93. And this actually this score is discriminate healthy people and MCI people. So early stage we can detect. And this is very interesting graph. Left side is using a pedicle method, and the right side without a pedicle. You can see here using the critical such kind of the phase alignment works very well. You can easy to feel. Okay, so I'd like to conclude today's talk. So basically, I show you 3 studies related to the gait recognition, and one is applied to the medical. And the first 3 is why we can do this kind of studies. We have one of the largest data set, OU-MVLP pose, and also OU-MVLP mesh. This kind of the data set is very useful for doing this kind of the research. And third work is still not so easy to extract patient's data. So number of the data set is smaller than this, but very important task. So I will show you today one of the application. So I show you. Okay, thank you very much. And if you have a question, I write here. Each classroom researcher will answer to your question anytime.
Okay, okay. Thank you, Professor Yagi. Any question here? Yeah, and maybe on page 47 or 46. So
46, right?
yeah.
This?
The previous one? Oh. Yeah, and the inputs, what's the input? Is the depth image or the clipped RGB image?
This is a clipped RGB image.
Clipped RGB image.
Any type of the image is of course okay.
So, and the next one, the next page, and there's a ground truth.
Yeah.
How to clarify the ground truth? I mean, how to definite it?
This is actually annotator one's result. Annotator second. Actually, this is A is the annotator resolve. So this is annotated dependent. There's some errors caused by annotated dependent. So what we did is we model the annotators model.
So that is not universal branches.
No, not universal ground, but we can estimate the annotator's skill. So what I show you is we can estimate the model the annotator skill. If we do not estimate the annotator skill, pattern is there's some difference. But we can estimate the annotator skill. We can easy to know.
Maybe the ground truth is subjective or objective.
This is actually annotated subject.
Very similar in the facial expression recognition. Facial expression recognition, they also very subjective.
Maybe a more subject problem, and it depends on the person. Such kind of the problem, if you apply this kind of technology, is very useful.
For the last research and the BCN, so to me about the results, it's very good.
Yeah.
So, I mean, this is only how to create the data set or the.
We collaborate with the medical school. And all of the MCI and the dementias is the patient's data, and so not using the MMSE score, such kind of the one.
Oh, okay. So the data set also is not a universal data set. It's just created maybe by yourself or by your research cooperator.
Yeah, that is we have this work is a collaborator is a medical doctor. So maybe I write. There's many names.
Yeah.
Then from here to here, all of them is a medical doctor. Our university medical doctor.
Okay. Thank you very much.
They support we can do.
Thank you.
Okay. Any other question? I have a question.
Yeah.
Yeah. In these years, large model, large vision model, or large language model, they are very popular. So
yeah,
what do you think in gait recognition or gait analysis? If how to use the larger models for
of course, generative AI can be generate a different type of the working style. So such kind of technology, of course, can be used for training or create a training data set.
Okay.
But maybe one of the problem is physical condition cannot guarantee, even if created. So sometimes humans arm is bent to this direction or something like that. So of course, such kind of the how to say physical control is required, but very good way to use such kind of generative AI.
Okay.
But that is close to the simulation-based approach.
Okay. Okay. Thank you. Any other questions?
So I think in like CB, we always use 2D camera. And
sorry, what the CB?
Computer vision.
Okay.
2D camera, but if we in biometrics, we use face or fingerprint, they are like 2D texture.
Yeah.
But in Gait, I think it is more like a 3D.
Yeah, that is a dynamic information. Yeah.
So do you think that using 3D sensors will improve?
Yeah, of course, 3D sensor is one of the tool, but of course your team create a 3D data set. That is one of the solution. It depends on the application. So someone said, commercial people said, if you use a 3D sensor, price is higher than the 2D cameras. So from viewpoint from the monetize, a little bit expensive. So it depends on task, I think. Then, for example, autonomous car,
Oh, yes.
3D data, wave, I forgot the name of the microwave is often used. Well, of course, resolution is not so high. But if low resolution, such kind of microwave can be used for gait recognition, don't need a camera. Normally, recent autonomous vehicle requires a camera and microwave. But if you don't have to use a camera, only microwave, in that case, make more cheaper.
Yeah.
So low resolution is a maybe point.
Yeah. I can introduce a little bit. This is Mr. Ye. He's my student. He currently is an undergraduate student.
Okay,
and,
okay.
He's working on his final year project.
Oh,
on
it's
gait
good. It's
recognition
good.
using LiDAR.
Ah, it's good. It's good.
So, any other question? Oh, the last question. Yeah, okay. If we have no question, I think we can stop here. And if you have more questions, you can email Professor Yagi for answers. And you can, yeah, I think the email can be searched online.
Yeah.
Okay. Let's thank Professor Yagi again for the great.
Thank you.